Hello and welcome to week 8, lecture 41 of the course Computational Complexity. In the past week, we saw circuit complexity classes. These were languages that could be decided by circuit families. So we saw P by poly corresponding to circuit families of polynomial size, and then AC and NC hierarchy, where the circuits were restricted to polynomial size, but there are also restrictions on the depth of the circuit, right? So NCI had, for instance, depth at most log n to the power I. And AC was similar, but then also allowed unbounded fan-in, right? So we saw some languages that that were contained in AC and NC, and then we also saw that parity, for instance, was in NC1, but then I mentioned that parity is not in AC0. And today we will see the proof that parity is not in AC0. So therefore, proving that actually AC0 is not equal to NC1. Right? So this is one of the rare situations where we have a unconditional separation. Right? So there is AC0 is not equal to NC1. We know for sure that these two are not equal because we have a language that is in one of them but not in the other. Right? And most of the results that we saw, right, and most of the results that are there, even the ones that we did not see, in the case of complexity theory, and particularly also in the case of circuit complexity theory, are somewhat conditional, right? So they say things like Carl-Clifton theorem. So it says if SAT had polynomial size circuits, then polynomial hierarchy collapses, right? It says if this thing happens, then something very unlikely happens. So this thing is very unlikely to happen as well, right? So that's why SAT is unlikely to have polynomial size circuits, right? And right, so ideally, when circuits complexity theory evolved as a field, perhaps the original hope was to find an answer to P versus NP, right? This is like in the case of many subfields of complexity theory, right? So one way to do that would have been to show that some some language like SAT does not have polynomial size circuits. Since we know that P has polynomial size circuits, this would imply that P is not an NP, right? However, unlike like I just said, we have Carl-Clifton theorem, which gives a conditional statement to the effect why SAT cannot be why SAT may not have polynomial size circuits. We do not know if any unconditional results of this type this type that will allow us to separate P versus NP, right? So in fact, the whole area of circuit complexity theory, I've heard people tell me that if you look at the kind of results that have come out of this area, and if you look at the kind of people who worked on it, smart, brilliant people, and the amount of time they put into it, the amount of results that we have is very not in proportion to the amount of work that has gone into the area. So it's an area where it's incredibly hard to get concrete results, right? So what we will see today is a rare circuit lower bound, right? Especially lower bounds are very hard. So we will show that lower bound meaning some language cannot be computed in a certain complexity class or in a certain algorithmic class, right? So like I said, we don't have any results stating that SAT is not in polynomial size. So now let us try to, in the hope to get something, let us try to restrict the class of circuits even more. Is there a language in NP such that a restricted class of circuits cannot, it is not in a restricted class of circuits? So, so what we will do, let's say that is restricted so much so that it is allowed to have only constant depth. Now, is there a language in NP? And the answer is yes. So the answer is yes, and the answer is parity, right? Parity means it's the class of all strings that have an odd number of ones, right? Or if you can compute it as a function as well, but you can also view it as a language. So all the strings that have all the binary strings that have an odd number of ones. And we will show that this language is not in the class of circuits that have polynomial size and constant depth. So AC0 is this class, which have, just to remind you, this has polynomial size, right, and constant depth, and uses AND, OR and NOT gates of unbounded fan-in. Right? Obviously, AND and OR gates of unbounded fan-in, NOT gates have fan-in 1. Right? And we will see that parity is not in AC0. And just to reiterate, parity is sometimes denoted with this O plus symbol inside the O, right, inside the circle. It is as a function. You can view it as a function. It is a Boolean function from 0,1 power n to 0,1. So I think mostly through this proof we will be viewing it as a function, not as a language. Right? Parity of a string, like a n-bit string, is 1 if and only if an odd number of input bits are 1. So parity of 0, 1, 1, 0, 1 is 1, whereas parity of 1, 0, 1, 0, 0, 1 is 0. Right? Because the first one has an odd number of 1 and the second one has an even number. Right? So okay, so this is the parity function. Right? So it's a very simple function, and in the previous lecture we actually saw that you could have a NC1 circuit, right? Which means it's a circuit of log n depth that can compute this. So we just noted that we could have a log n depth tree where each consisting of the parity gate itself, right, where each branch is each gate is a 2-bit or 2-input parity gate, and this can be used to build a parity n function, right, and each of these parity gate has a constant size implementation using AND, OR and NOT gates. So that is why parity is in NC1. Okay, right. So as I said, it was kind of a nice big result at that time, and there are many proofs of it, and we'll be seeing one of these proofs. I'll explain more about the proofs as we go along. Right. So why is this, like, one intuition as to why this is a good function to demonstrate not in AC0, right? Because a constant depth circuit of polynomial size, right? So it has polynomially many gates, or it could have up to polynomially many gates, but it is constant depth means it has n inputs, but then constant depth means it's a rather flat circuit. So and since you have unbounded fan-in, you would expect it to like either be independent of many inputs, or if it is dependent on all the inputs or the majority of the inputs, then the gates that are there would be rather very wide, right? Otherwise you cannot really compute using only constant depth, right? In very few number of levels, in a constant number of levels, you must complete the computation. So either you are ignoring many inputs, or you're actually accounting for all the inputs, but then they are all very broad gates that have huge fan-in. But if you have a gate with a huge fan-in, and recall that we only have OR, NOT and AND gates, right? So OR gates and AND gates that are the ones that can have huge fan-in. But if you have a huge fan-in, even one, if you have a huge fan-in OR gate, even one input being 1 fixes the output to be 1, right? So the other input flipping doesn't really change things. Similarly, if you have a huge fan-in AND gate, even one input being 0 fixes the output to 0. If some other input bits flip, then the output will not change. So the point is that there are a lot of, for any input x, or for any combination of the input bits, there are most of the other bits, if you flip, it is unlikely to change the output, right? So, and what I'm talking is in general for any function that can be computed using a constant depth size circuit, a constant depth circuit. So either a lot of inputs are ignored, in which case what I said still remains true, or even if they are not ignored, they are part of huge fan-in gates. So which means it's very unlikely that the output flips when a specific input bit is flipped, right? So this is the intuition. This is saying that most of the input bits, when you flip it, it doesn't change the output. So that gives us an intuition why parity is unlikely to be in this class, because parity function is such that it depends on the number of input bits being, and if it is odd, then the output is 1. If it is even, the output is 0. So whatever be the input, right? So here I said two. I said two strings and the parity was 1 and 0. So just one input bit, when I flipped, the output flipped, and this is true for any input bit. If I had flipped the last bit, for instance, I would have got 0 1 1 0 0. Again the output flips, right? Because it depends on all the inputs, and it also flips when you flip any input. So that is one intuition as to why parity is unlikely to be in this kind of circuit with constant depth, right? And this coming to the statement, it's just simply saying that parity is not in AC0, and it has been proved by many people using different techniques. So the first proof was by 3 people, first Sachs and Sipser, right? Then I-Type gave another proof later, then Yavo gave another proof later, then Hostad gave another proof, and then the proof that we will see today is by Rasparov and improved by Smolensky in 87. Okay. So in fact the strongest result is by Hostad. This is the strongest result in terms of the bound that we will get. Okay. Whereas Rasparov's and Rasparov-Smolensky's result that we will see today, the proof of which we will see today, actually gives a slightly lower, slightly inferior bound, but it has some other features, okay, which maybe if I have time at the end of the lecture I will explain. Okay. Okay. So let me just state what Hostad says and what Rasparov-Smolensky says. Right. So parity is not in AC0 is what it implies, but I will just state it. So what Hostad says is that any AC0 circuit that computes parity must have size 2 power order n power 1 divided by d minus 1. Okay. So this itself is a bit of a strange statement, because AC0 implies polynomial. So by AC0 circuit I mean any, maybe I should just rewrite it. AC0, instead of that I should say any constant depth circuit using AND or and NOT gates. Using AND or and NOT gates. Using AND or and NOT gates that computes parity must have size at least this. So this is obviously not polynomial. 2 power n power 1 by d minus 1, right, where d is the depth of the circuit, right? So if the depth is 2, then this implies 2 power n must be the size, or 2 power order n. When depth is 10, this implies something, right? And for depth is 3, then this implies 2 power square root n, for instance. And what Rasparov-Smolensky proved is slightly weaker, in sense that they gave the lower bound, that is 2 power n power 1 divided by 2d. Okay, so there is a 2 factor in the exponent of n. The n itself sits in the exponent of 2, but there is a 2 factor here which is not there in Hostad's bound. But we will see the Rasparov-Smolensky's proof. We will see this proof, right? So before getting into the proof, it probably helps to get a feel to what we can do with a fixed depth, right? So what can we compute with, let's say, a depth 2 circuit? Depth 2 meaning any from the output to the input there are only 2 gates. Any path if you take from the root of the tree which is the output gate to the leaf which is usually the inputs, there are only 2 gates, right? So one thing to note is that any Boolean function has a CNF or a DNF approximation. CNF, we have already seen CNF in this course. CNF means it's an expression using AND of ORs, right? So it's an AND of ORs, and DNF is an OR of ANDs. Okay. So for instance, DNF function, let's say we have three bits and you want to compute the parity. You can just collect what are so called the min terms. Okay, so for which are the situations where the so in other words, you can just look at the truth table and gather all the situations where the output is 1. So the parity function is 1 when you have exactly one input bit equal to 1, or exactly 3 input bits be equal to 1, right? So the one input bit equal to 1 is the first 3 terms here: x1, x2 complement, x3 complement, this one. Then x1 complement, x2, x3. This is the second term is when x2 is 1 and the other 2 are 0, right? The third term is when x3 is 1 and the other 2 are 0. And the last is when all 3 are 1. So the first term is set only when 1 0 0 is the input. Second term is set only when 0 1 0 is the input, and so on, right? So it is just basically breaking down the input into each possible scenario, and each term is capturing a specific input, n bit input, and then you are taking an OR over all the n bit inputs. So again, I have used a different notation here. So plus denotes OR, and if I just write it side by side, it is multiplication. So this is a DNF expression for parity over 3 bits. And you can get a CNF expression by taking the negation of parity and then taking the complement using De Morgan's laws. This may sound a bit confusing, but let me just. So what is the negation of parity? It is all the terms that are not here, right? So the first term here, x1, x2, x3 complement, is true when the input is 1 1 0. Second is true when the input is 0 1 0, sorry, 1 0 1, right? Third is true when the input is 0 1 1. So basically all the cases when there are 2 1s, and the last term is true when the input is all zeros. So this is the negation of parity, and this is a DNF expression for that. And we can get a CNF expression by just taking the complement of this and using De Morgan's laws. So De Morgan's laws simply says that an negation of an AND function is the OR function of the negated things, and negation of an OR function is just the AND function of the negated things. So if you take a complement over this, right, I think this is what I have tried here with the red big red line. First, the red line. First, we have the AND of each of the negation of these things. So we have the AND of x1, x2, x3 complement, which actually further breaks down into the x1 complement or x2 complement or x3, and then you have an AND where you have x1 complement or x2 or x3 complement, and so on. You get this. So you have, this is what we have is the CNF form for parity, and you can verify that this is indeed the case, right? It's basically you have 4 terms and the AND of the 4 terms, and each of them will become 0 for a certain specific input when for a certain specific input, at which point the output will be 0. If the input is none of these 4 specific inputs, then the output will be 1. So this is a DNF for parity. Again, this is an AND of ORs and OR of ANDs. So both of these, the DNF expression over here as well as the CNF expression over here, right? Both of this is a CNF for parity. Both of this can be expressed as depth 2 circuits, right? It's again, we have unbounded fan-in, so it's not very difficult to see how you can express this as depth 2 circuits. Again, if it's not clear, you can work this out. Why, how you can represent as depth 2 circuits, because it is what I've written here, right? So here, how many terms are there? It is 3-bit input and you have 4 terms. So the depth 2 circuit, either if it is CNF or DNF, will have 2 power n minus 1 gates. So it's 4 here when you have 3 input bits. If you had 4 input bits, it would have been 8. 5 input bits, it would have been 16. So it's 2 power n minus 1 gates. And what does Hastad say? Hastad says that if depth is equal to 2, then it is 2 power order n. The d2 minus 1 is 1, so 2 power order n, which is what we have here. 2 power n minus 1 is roughly 2 power order n. So this matches Hastad's bound, right? The next thing that we could possibly consider is depth 3 circuit, right? So what we can see here is that when you have a depth 2 circuit, of course you can compute parity, but then the size of the circuit becomes so huge. We need 2 power n minus 1 gates, which is exponentially many, which we cannot have, right? So this is what happens in the case of parity and depth 2. Let's see what happens when you have depth 3. One way to do it is to consider a 2-level tree for parity, right? So you compute parity of the first k bits, then the next k bits, and so on. So like in blocks of k input bits, right? First block, second block, and so on, and then last block, right? Each block has k bits, and then you have a top level gate which takes the parity of these parities. So this is it's just a hierarchical thing, and the parity of parity is also equal to parity, and this uses n divided by k plus 1 gates, right? So n by k plus 1 gates, one top level gate and n divided by k gates at the second level. Now what we could do is, the top level gate I could implement using DNF. Okay, DNF means it is OR of ANDs, this expression, the first one is written in green, and the second level gates I implement all of them using CNF, which is AND of ORs, like this kind of expression, the expression in red. So therefore what we will have, so the OR of ANDs will need depth 2 and the AND of ORs will need depth 2. So one may think that this is depth 4, but actually it is depth 3, because I could merge these AND gates from the DNF and the AND gate from the CNF. I could just make the AND gates, design it appropriately so that you can combine them into one AND gate or one set of AND gates, right? So it will be OR of AND of ORs. So whenever these AND 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 are appearing nearby, these AND and AND, these ANDs can be merged to just have one layer of AND gates. So it is just an OR of AND of OR circuit. This is again something that you can check, right? So this will be depth 3 circuit, and what will be the size here? The size here will be optimized when, so this was our starting point, recall, you do it as k blocks, and so this is block 1, block 2, not k blocks, n by k blocks, right? Block n divided by k, each block had k inputs. So, and the number of gates will depend on the number of blocks. So here we have n by k plus 1 gates is what I said, but this is parity gate, and unfortunately this is not a gate that is available to us. What we have is just AND and OR and NOT gates, of course. So the point I want to make is that the size will be optimized when it will be when k and n divided by k are minimized. So the DNF or CNF both will, the first one of them will use k gates, the other one will use n by k gates, right? So we have to minimize this function, k or n by k. And what is the k that will minimize this? The minimize both of them. It will be balanced when these two are equal. That will happen when k is set to square root n, right? K is set to square root n. And then in that case, the size will be exponential in square root n, which is 2 power square root n. Right, this is the size, and this can be generalized to a depth d circuit where you can have d, basically d minus 1, you can start with a d minus 1 tree of parity, and you could implement them alternatively with DNF and CNF, and therefore you end up merging all the, like, OR of and you can merge, OR and OR you can merge, and at the end you will end up getting a so d minus 1 parity gate tree is what I said, and at the end you will get a depth d circuit. Okay, so maybe I'll just write that as well. Start with a d minus 1 depth tree of parity gates, and then convert into DNF, CNF alternately. And again, this is optimized when at each level of this thing, the parity gates take in as input the d minus 1th root of n, right? And the depth of this entire circuit will be 2 power the d minus 1th root of n, which is what we have written here. 2 power the d minus 1th root of n, and that exactly matches with what Hostad gave us. It is 2 power the order d minus 1th root of n. Okay, right. So till now we have been just talking about the importance of circuit lower bounds, and then now we have seen what will happen when we try to have a constant depth circuit that computes parity. And what we are seeing is that when the depth increases, I am able to control the size, but still for a constant depth it is still exponential size, right? But this is not a proof. Like, maybe we are just limited in our creativity. Maybe these ideas are the very simple, straightforward ideas. Maybe there is some very extremely clever idea that looks nothing like this, but somehow manages to compute the parity function, right? So this is the issue that all lower bounds have to deal with. You have to rule out all possible circuits, or in the case of algorithm, you will have to rule out all possible algorithms. How on earth can one rule out all the possible algorithms or all the possible circuits in this case, right? So maybe there are extremely different clever ways to make the circuit, and maybe we are not. And how do we make sure that our proof rules out each and every one of these possibilities, right? So that is the reason why these bounds are hard. That is one of the reasons why these lower bounds are hard. And this particular proof is extremely interesting, and we'll use maybe 2 or 3 different techniques that you may or may not have seen, but they're extremely clever, and one could actually be surprised as to how it was thought that we could use these techniques to solve these to obtain these lower bounds, right? Again, this proof was by Rasborov and Smolensky, right? So the proof will rely on representing the parity function using a polynomial. Okay, in fact, it will rely on approximating this parity function using a polynomial, right? So I'll say what I mean by representing using polynomial or approximating using polynomial, right? And we will actually work on the F3 field. So F3 is the field which has only 3 elements, 0, 1 and 2, and everything happens in the modulo 3 sense. Okay, so the easiest way to think of it is you only have 0, 1 and 2, and everything happens in the modulo 3 sense. So 1 plus 1 is 2, but 2 plus 2 is 4, but 4 is again 1. 2 plus 1 is 3, which is 0. 2 times 2 is 4, which is again 1. Right? So you understand how multiplication addition happens, both happens modulo 3. And the very high level outline of the proof is that any AC0 function can be approximated by a low degree polynomial. Okay, so any function that can be computed by an AC0 circuit, you have a low degree polynomial approximating it over F3. Okay, so over F3. This is very important. But the parity function needs a large degree over F3. Right? It actually turns out that even to approximate it requires a large degree. So, and that results in the contradiction. One is saying that every AC0 function requires can be approximated using a small degree polynomial. But parity, however, requires a large degree. So, if parity were representable as an AC0 function, this would mean that this would lead to a contradiction. So, that is the very high level idea of the proof. So, now I will explain what I mean by representing and approximating Boolean functions by polynomials. So, this is kind of a sometimes it is called arithmetization. Okay. So, we are going from, or we are moving from a Boolean world where there is only 0, 1 to some other world where there are maybe other things like a real number, or in this case F3. But like in the Boolean world there is no multiplication, squaring, such things are not there. Addition, subtraction are not there. We only have ands and ors. But in the world of arithmetic world, you have addition, multiplication, squaring, division. All of these are there, right? So we'll see what it means to represent a Boolean function using a polynomial. So suppose the Boolean function is f, right? N bit input to a 1 bit output. We will try to represent it using a polynomial f tilde over f3. So very simple way to explain is the AND function is simply the product, let's say AND function of over x1 x2 up to x3 xn, right, and over x1 to xn. This can be represented by the polynomial which is just x1, the product of x1 to xn. Okay, so what we want is when the input is from 0, 1 power n, when the input is of a Boolean type, then we want the output to be what we expect. So if you see, when the input is 0, 1, if at least one of the input bits is 0, the output will be 0, which is what we want in the case of AND. And when all the input bits are 1, the output will be 1, which is again what we want in the case of AND. So this is the AND function. How can you write the OR function? So OR is not so straightforward, but one thing we can do is to kind of use the De Morgan's laws. De Morgan's law says that negation of AND is an OR of negations, right? So you can write AND as, so basically you can write OR gate as an AND gate, negated AND gate, and where each input is negated as well. So you negate the inputs, you make an AND, and then negate the output. So which gives us this expression 1 minus x1, 1 minus x2 dot 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 1 minus xn. So you can verify this, right? In the OR situation, we want the output to be 0 when all the inputs are 0. So suppose x1, x2, all of them are 0. Then 1 minus x1, 1 minus x2, all of them will be 1. So the product here will be 1. So 1 minus the product will be 0. So when all the input bits are 0, the output is 0. When at least one of the input is 1, let's say x1 is 1, then 1 minus x1 becomes 0, So this becomes 0. So this entire product becomes 0, and 1 minus 0 is again 1. So even if at least one of the input bits are 1, the output is 1, which is what we want in the case of OR. So both AND and OR have representations using polynomial. But these representations, you can see that the degree of the AND representation, the degree is n. And even for the OR representation, the degree is n, right? Because if you just compute there is a x1, x2 up to xn term that is there. Right? It might have some coefficient plus or minus 1, but there is such a term that doesn't cancel out with others. So these are ways to and this in when the input is from the 0 1 range, or not even range, when the input is consisting of only 0 1 vectors, then we get the desired output. But these are polynomials, so you can even apply them in when the inputs are not 0 1. So when x1 x2 everything is 2, then this gives us something, right? So you can even what I am saying is these are polynomials that have other outputs when the inputs are outside the 0 1 range. But the point is that we don't care about that. We only care about how they behave when the input is 0 1 vector. Okay, so for when the input is from this 0 1 vector, then we want the polynomial, which is f tilde, to be equal to the actual function. So again, we have seen two examples, AND and OR, and what are the corresponding polynomials. Okay, one important point is that the polynomial that expresses any Boolean function, right? So these are all Boolean functions, 0 1 functions. We may assume that this polynomial is multilinear. What does multilinear mean? Multilinear means that all the terms are of the form x1, x3, x5, or plus x1, x2, x6, x7. So meaning all the terms are like this, meaning there are no term which has x1 squared or x1 cube or x3 squared or x7 cubed, or all the individual terms, all the individual monomials have individual variables. None of them have degree bigger than 1. There are no terms with square or cubed or whatever. So the degree of x1 in any term will be at most 1, and so for any other variable. Degree of x2 will be at most 1, x3 will be at most 1, and so on. So every term will be just either will be of this type, either degree 0 or degree 1 for each variable. That's why it's called multilinear, right? Why this is the case? Why is this the case? This is because we are only bothered about 0 1 inputs and 0 1 outputs. So if you square x1 when input is 0 1, x1 is always, so xi squared is xi itself when xi is 0 or 1, and xi cube is also xi itself. So there is no point in doing that, right? So any polynomial representing a Boolean function, we can just consider only multilinear polynomials, right? The individual degree of any variable is at most 1. Again, I have said here again, we can replace xi cubed, xi squared, etc. with xi. So that is how we represent a Boolean function using polynomial. Now we will go to the notion of approximating a Boolean function with a polynomial. So now when I say approximate, it's a random thing that we will be doing. Suppose there is a distribution of polynomials. Okay, so there are many polynomials and we are choosing this from these polynomials using some distribution. Okay, and this is considered to epsilon approximate a Boolean function f. Okay, this is considered to epsilon approximate a Boolean function f if, this is the key word, epsilon approximate, if for any Boolean input, any 0 1 input, the probability that the function or the polynomial is not equal to the actual function value, this probability is at most epsilon. So this has to be true for all the input sequences. For any input x, what is the probability that the polynomial is not equal to the actual function value? And this probability is chosen over the distribution, all the polynomials in the distribution. So fix the input x. For that fixed input, what is the probability that the polynomial is not equal to the actual function? This probability must be at most epsilon. When this happens, we say that the random polynomial or the random distribution epsilon approximates the polynomial. Again, and this means if you take the negation, or if you for all x, the probability that the polynomial is equal to the actual function value, it is at least 1 minus epsilon, right? So it's just, I'm just taking the complement event here, not even the entire negation. Okay, and the first theorem that we will prove. So this is kind of more formal restatement of this. Every function in AC0 can be approximated by a low degree polynomial. So this is a more formal statement. If fx is computed by a circuit of size s and depth d, then there is a distribution from which we can choose a polynomial px, which is over the f3. Okay, so which has coefficients from f3, meaning coefficients 0, 1 and 2, and everything happens modulo f3, everything happens modulo 3 over the n variables, right? There is a distribution from which you can choose a polynomial such that the degree of the polynomial or the degree of the polynomials in the distribution is at most log s power the depth, and 2, the polynomials and the distribution 1 by 4 approximates fx. Okay, so the 1 by 4 approximate fx, which means that for any x chosen over the distribution, the probability that the polynomial and the function disagree is at most 1/4. Okay, so this is saying that if you allow 1/4 errors, then the size of then the degree of the there is a polynomial that approximates 1/4 approximates the function, such that the degree of the polynomial is at most log s power d. This is log s power d. So what we will do, so it seems a very it seems an interesting statement. The proof is rather direct. What we will do is to look at the circuit, AC0 circuit, and then we will just build the circuit using that. Basically, we will replace each gate with a polynomial, and then at the end we will just compose these polynomials to get a big polynomial, and each gate will be approximated by a polynomial. So the entire function will be approximated by the big polynomial, right? So maybe I'll say it at the end, or maybe I'll say it now. So suppose you have an AND of, let's say, 2 ORs, right? And maybe there is a NOT somewhere here. Maybe there is a NOT somewhere here. So we will use the NOT function to approximate the NOT, and we will use the OR function to approximate the OR, and the AND function will be used to approximate the AND, or the polynomial corresponding to the AND function, and that will take as inputs not the actual input but these polynomials as input. The variables in the AND polynomial will be replaced by the OR polynomials here and here. So it will be a polynomial of polynomials, which is still a polynomial. Okay. So this is what we will do. So we have already seen that the AND function of x1 up to xn has degree n, right? So this is not n factorial, this has degree n. Okay, when in math one has to be careful. This has degree n, and we also saw an OR function that had degree n. But unfortunately, the depth we are allowed to have is order log s power d, right? And recall we are dealing with AC0 functions. So s is polynomial, so log s will be log n, and d is constant, so log n power some constant. So this is something like order log n power some constant d, right? S is polynomial, so log s is like order log n. But so we cannot use these AND and OR functions. Both of them were degree n. So we will see how to approximate the OR function, right? And we will use that. Okay. So consider a very silly example. Consider one OR function which has very low degree, in fact degree 0, is to always output 1. So this polynomial, it's a polynomial that has degree 0. So OR of x1 to xn is just merely 1. Okay. Now what happens here? For all the 2 power n minus 1 inputs, this outputs the correct answer, right? Because OR of any combination is 1 except for the all 0 combination. But when the input is all 0, this is always wrong, and this is not desirable. We want, for any fixed input, the probability of the error to be at most 1/4. The probability of error should be at most 1/4. So this is not good, because for at 0 power n, the probability of error here is actually always there is an error. So let us try to find another approach. Okay, so this does not work. So consider the polynomial alpha xr, which is simply, so where x is the input and r is the random input. X is input vector, and r is a random vector. Random, let's say random vector from, it's all over f3. Okay, all the inputs, all the coefficients. Now inputs is, we are interested in 0, 1, but x can in general be over f3. Okay, so random vector is also from f3. So meaning the random, each coordinate of the random vector can be 0, 1 or 2. Okay, so what is alpha xr? It is just a linear sum. It is just x1 r1 plus x2 r2 plus etc. up to xn rn. Again, everything is over f3. Okay, so just think of it as mod 3. That is the simplest way to think of it. So suppose r is chosen uniformly at random from f3 power n. Okay, there are 3 power n possible choices of r, and each one of them is equally likely. Or in another way to look at it is, r1 is chosen independently at uniformly and independently from 0, 1, 2. r2 is chosen uniformly and independently from 0, 1, 2, and so on. Right? Each one of them, each coordinate is being chosen from 0, 1, 2 uniformly and independently. What is the probability that the OR function is equal to alpha? Okay, so for any x, let us fix an x and then look at it, and the probability being over the choice of the random string r. So one thing is clear, when x is the 0 string, alpha will always output 0, right? Because it doesn't matter what r is, everything gets killed. So alpha xr is 0 when x is the 0 input. What if x is not the 0 input? When x is not the 0 input, meaning at least one coordinate of x is 1, we want the output to be 1. So when x is not the 0 input, there is a coordinate j for which xj is not 0. If it is not 0, again recall that we are interested in only inputs from 0 1 Boolean input 0 1 power n. So there is a j for which xj is not 0. Now depending on the sum of the other, so what is alpha? Alpha is just summation over xi ri over all I equal to 1 to n. Now consider the summation of all the terms except the xj alpha j term, except the jth term. We know that xj is not 0. We don't know what alpha j is. So you look at the sum, you look at this sum, and we know xj is not 1. Now which alpha j will make the whole sum? So what will happen to the whole sum can be just changed by changing the value of alpha j, right? For instance, if the rest of the terms sum up to 1 and xj is equal to 1, if alpha j is 2, then the whole summation is 0, right? So in other words, maybe I'll just write it here. Alpha xr is the sum of everything else I not equal to j xi. Okay, there is an error here. It's xi ri. Xi ri plus xj rj. What I am saying is that whatever this summation is, now depending on, we know that xj is not 0, depending on the value chosen by rj, we can always make the total sum 0 with for a specific rj. Okay, so there is only one choice of, okay, this is again an error, one choice of rj for which alpha xr becomes 0. The whole sum alpha becomes 0. And this is an undesirable situation, right? We are trying to compute OR, and we know that x is not all 0, which means at least one bit is 1. And we want alpha to be not 0. So there is the problem is there is one choice of rj for which alpha is not 0. So for which there is exactly one choice of alpha for which alpha is 0. There is exactly one choice of rj for which alpha is 0. Okay. So just to summarize, when x is not the all 0 vector, there is the probability that alpha is not 0 is 2 by 3. Right? For the other choices of rj, alpha will not be 0. But notice alpha is a polynomial. So when it is not 0, there are two other possible values it can take. We are all working over f3. So it could be 1 or it could be 2. Right? When I say 0, not 0, it could be 1 or 2. Alpha could be 1 or 2. And we don't like 2 because we are trying to approximate or represent a Boolean function. So we want the output to be 1. So from the but we know it is not 0. So at least so far so good. How do we get from 1 or 2 to always 1? So what we do is a very simple thing. We just take the square of alpha. Okay. So the point here is that 1 square is 1. And 2 square in the mod 3 world, 2 square is 4. And 4 mod 3 is also 1. So both ones, if it is regardless of whether it is 1 or 2, its square will always be 1. So alpha, whenever alpha is not 0, alpha square will be equal to 1. Right? So which means I can again rewrite when x is not the all 0 input, the probability that alpha square is equal to 1 is equal to 2 by 3. Right? So alpha was a degree 1 polynomial, right? Alpha square is a degree 2 polynomial, and when x is 0 there is no error, right? When x is 0 we already saw that it always outputs 0. When x is non-zero there is an error there is an error, with probability 1 by 3 it may give 0 value. So overall alpha XR is a degree 2 polynomial, right, with error at most 1/3. Okay, what we wanted is a general approximation for any function with error at most 1/4, and this OR is going to be a building block. But so we have some representation with error 1/3, at most 1/3. How do we improve the probability of success or decrease the probability of error? Well, we have seen this in the case of randomized algorithms, right? We just repeat. We keep repeating it and then boost the probability of success. So suppose you do several alphas or several alpha squareds, each alpha having a separate set of random bits. How many? And then what do? You output. So you know that when the actual output, intended output is 0, there is no error. It always outputs 0. The error happens when the intended output is 1, and sometimes it outputs 0. So any one of these outputs being 1, we want to output 1. So we again use the same trick. You do 1 minus alpha square, 1 minus alpha square, etc. and k such times. 1 minus alpha square with r superscript 1 being the first set of random bits, r superscript 2 being the second set of random bits, and so on. So there are k such sets, and you can check that if any alpha square x ri is equal to 1, then this whole thing I am calling beta, then beta xr is equal to 1, or rather it's if and only if beta xr will be 1 if and only if this happens. So this you can check, that is, so you have 1 minus 1 minus 1 minus everything, take the product and then 1 minus that. So again, this is like the similar De Morgan idea that we saw earlier, which is in other words it's again the same thing that I have written here. Beta is 1 if and only if there is an I such that alpha squared, the ith alpha squared entry is 1. Now what is the probability that, so the only probability of error now happens when all the k trials, all the k times you get the wrong answer. The intended answer is 1, but you output 0 in all the k times. So what is the probability of error in one trial or one alpha? It is 1/3. We saw that it is 1/3. So the probability of the beta erring is at most 1/3 power k. So now you can see how the improvement is coming. So and the degree is simply alpha is of degree 2. So beta is, you have k alphas multiplying. So beta's degree is 2k. Now what must k be so that, or what must the degree be so that the error is sufficiently low? So we want to bring the probability of error to some epsilon, let us say. Okay, we want to bring the probability of error to some epsilon, which means 1 by 3 whole power k should be epsilon, which means k should be order log of 1 by epsilon. And the degree, so again k is, the degree of beta is just twice k. So which means the degree of beta also should be order log 1 by epsilon. So if you want a epsilon approximation, you better take degree order log 1 by epsilon, which is still okay. Epsilon is some constant, so it is still not dependent on n, etc. So order log 1 by epsilon. Okay, so now we have seen how to epsilon approximate for any epsilon the OR function using a order log 1 by epsilon degree polynomial. This is our main building block, and it turns out that this is enough. Okay. So now what we have done is we have epsilon approximated or with a degree 1 order log 1 by epsilon. How do you epsilon approximate not? Not is you can easily directly represent this. You don't even need to approximate. Just take 1 minus xi. Again, not is always fan in 1, so you just take 1 minus xi. And how do you represent and? We do the De Morgan trick. The and is so and can be represented by take the or, all the inputs also have NOT gate, and the output also has NOT gate. So this is how you represent and. And since we know that the NOT gates do not have any error, the error of the AND gate will be same as the error of the OR gate. Whenever there is an epsilon error in the OR gate, that could result in epsilon error in the AND gate. And whenever the OR gate computes without error, the AND gate also will compute without error. So AND gate also can be computed or epsilon approximated using degree order log 1 by epsilon. Now, so we have seen how to epsilon approximate for any epsilon, OR gate, AND gate and NOT gate. NOT gate, of course, there is no error. What did the theorem want? Theorem wanted to 1 by 4 approximate any function with a log s power d degree. So let us see how that happens. How do you 1 by 4 approximate a general depth d size s circuit? So three things: 1 by 4 approximate, depth d, size s circuit. So what we do is we have some circuit, right, which is an AC0 circuit, depth or some depth d size s circuit, not necessarily AC0. Let's say the circuit has AND gates and OR gates and NOT gates. We know how to epsilon approximate each one of them, right? So the idea is epsilon approximate each gate, right? You look at the circuit, you epsilon approximate each gate. Now, what does it mean? So suppose there is a polynomial, let's say p here, that takes as inputs polynomials, let's say some minute or q, some q's, then let's say q1, q2, etc., q1, q2, etc., qk. Then what it means is that the polynomial takes as input p of q1 of some x or whatever, q2 of maybe some x2, something like this. So basically it's a polynomial of polynomials, qk of xk, right, something like this. So what I'm saying is how it's just a composition of polynomials of other polynomials, so the degree will blow up. So let us try to estimate the error and the degree for this. So this is a size S circuit. Each one of the gates we are replacing with an epsilon approximation. Okay, so each of one of the gates has, for any fixed input, right, for any fixed input can result in an error with probability at most epsilon. So there are S gates, each causing an error with probability epsilon. So total probability of error is at most epsilon times S. So this is the union bound. An error could happen in this gate, another error could happen in this gate, but these errors could even coincide. But the worst case is that each error happens in a separate eventuality, separate outcome, So, so the worst case is when the probability of error is at most epsilon multiplied by the number of gates, right? So the total probability of error is at upper bounded by epsilon times s. What is the total degree? So whenever you do this kind of composition, like I said here, p of q or whatever, the degree of the resulting polynomial is the degree of p multiplied by the degree of q. So to see why, so suppose it is like saying I am computing x power n1. Now I am replacing x with some y power n2, right? So I am replacing x with, so maybe I will just write it again, x power n1 and replace x with y power n2. So it is like y power n2 whole power n1, which is nothing but y power n1 n2. So the degree is actually multiplying. So n1 and n2, they multiply. Okay. And when you have depth d, you could have up to d levels of such recursive polynomial. So and we know that at each level the degree is order log 1 divided by epsilon. So it is order log 1 divided by epsilon multiplied by order log 1 divided by epsilon and so on, d times at most, because depth is d, right? So it is simply order log 1 by epsilon whole power d, right? That is the degree. Okay, so for this construction the error is epsilon s and degree is order log 1 by epsilon whole power d. Okay, now what was the target again? The target was to show that for any size s and depth d circuit, right, you can 1 by 4 approximate it using log s whole power d polynomial. Okay, so 1 by 4 was the target error. So if the target error is 1 by 4, then all you need to do is epsilon s should be 1 by 4. So we set epsilon to be 1 divided by 4s. Now we plug this value of epsilon into the degree. So 1 by epsilon is 4s, or so you can just replace 1 by epsilon by 4s here. So order log 4s whole power of d. But log 4s is simply log 4 plus log s, which is simply 2 plus log s. But then anyway we have the O notation which can absorb that. So it simply boils down to order log s whole power d. So what we have here is what we set out to prove. What was that? This was that we have a polynomial or polynomial chosen from a distribution, right, of degree order log s whole power d, that 1 by 4 approximate fx. So fx is any polynomial, sorry, fx is any function that can be computed by an AC0 circuit. We have shown how a polynomial chosen from a polynomial family from a distribution can 1 by 4 approximate it, and where the degree of the polynomial is log s whole power d. So this is how we get that. So this is like the first kind of this first bullet point here. Every AC0 function can be approximated by a low degree polynomial over F3. Now I will just say one more thing and then conclude this lecture. Okay. So what we saw was a polynomial chose a distribution from which you can choose a polynomial that has bounded error. Now let us change the error around. So till now we had error defined as for a fixed x, for a fixed input x, the error was over all the choices of random bits. Now instead, let me just not have any randomness. Let's fix a polynomial and look at what is the, if you just vary the inputs, now what is the probability of the error. So now the claim is that suppose you have a function f, okay, function f computed by an AC0 circuit or circuit of size s and depth d. Now we are claiming that there is a fixed polynomial q, okay, that has degree order log s whole power d, which is the same as what we had in the previous theorem, such that the probability of qx equal to fx is at least 3/4. And in this probability, please note this, probability over inputs, not, there is no randomness here, or the randomness is over the input choice of input. The polynomial is fixed, this is fixed. So in the earlier case, we showed a distribution of a family of polynomials and a certain distribution, such that if you choose a polynomial from that distribution, the probability of error for any input x is at most 1/4. Now we are saying that there is a specific polynomial, there is one polynomial, okay, we are not saying how to find it or anything. There is one polynomial that has the same degree, log s whole power d, such that if you just vary the input, if you choose the input randomly, the probability that the polynomial is not equal to fx is at most 1/4, or the probability that the polynomial equal to fx is at least 3/4. Okay, and this just follows from the earlier theorem, and it is very simple and easy to see, so it's rather short. So the earlier theorem gave us a distribution. Whenever the polynomial is chosen from the distribution, the probability that p is not the same as the polynomial is not the same as the function is at most 1/4. Okay, so now let us make the following matrix. Okay, so each row is indexed by an input sequence. So assuming we have n input bits, we have 2 power n possible inputs that we are interested in, all 0 input going to all 1 input. So I am representing them as x superscript 1, x superscript 2 and so on. And these are the rows are the inputs. The columns are the various polynomials that are there in the distribution. So I don't know how many polynomials are there. And the entries are 0, 1. Okay, what do they indicate? 0 indicates that there is an error. So this 0 at the top right or top left, sorry, indicates that P1, the polynomial P1 computed at the first input x superscript 1 is not the same as the function at x superscript 1. And this 1 that says that the polynomial 2 at x superscript 1 is equal to the function at x superscript 1. And likewise we can fill up the matrix. What do we know? We know that, what did the theorem say? This theorem says that for any input, right, let's fix an input x1 or x10, the probability of the polynomial, the polynomial is chosen from the distribution, right? So from the columns, the probability that a certain the probability that the polynomial chosen from the distribution gives an error is at most 1/4, or it agrees is at least 3/4, which means that you fix an input, let's say xj, it may have some 0, some 1, something, right? So it may have 0, 1, 0, 0, 1, 1, something. When does it have a 0? It has a 0 when the polynomial does not agree with the input, or sorry, the function. 1 when the polynomial agrees. We know that once you fix the input, the probability that the polynomial agrees is at least 3/4. So which means in this row, it contains at least 3 by 4 fraction of ones. Right? This is what I am saying here. Number of ones in that row is at least 3 by 4 fraction. Now I can say this for any row. First row has at least 3/4 fraction, second row has at least 3/4 fraction, and so on. Right? Which means that if you look at the matrix overall, the entire matrix, at least 3/4 of its entries are 1. Right? If you look at the entire matrix, at least 3/4 of the entries are 1. Okay, so this matrix is 75% ones. Now let us change the perspective. Now let us try to look at columns. Okay, I know that there is a matrix with entire fraction of ones is at least 75%. Now all I am saying is that there is at least one column that has 75% ones. Right? All I am saying is that there is at least one column that has 75% ones. Why is this true? This is true because we know that 75% of the entries are ones. If there is no column with 75% ones, that means all the columns have less than 75% ones. Let's say all the columns have 70% ones. That means the total fraction of ones is also in the entire matrix is also 70%. That's a contradiction. So there must at least be one column with 75% ones. In fact, there may be more than that. Right? So now let's say that column is Pi. Right? This column is Pi that has 75% ones. This means that the polynomial, so this column is a polynomial, right? This Pi has 75 or 3/4 ones. Which means for this particular polynomial Pi, 75% of the inputs, this polynomial Pi gives the correct answer on 75% of the inputs. Right? This column corresponds to Pi. Now you choose that polynomial. So the theorem says there is a polynomial Q which agrees on the function, agrees with the function on 75% of the inputs. So choose Pi to be that Q. That has at least 75% ones, which one means an agreement with the actual function, right? So that shows that there is a polynomial, right? So again, the statement is that if there is a function f that can be computed by a circuit of depth d and size s, there is a fixed polynomial. Now there is no distribution over f3. Again, we are still over f3, such that the degree is order log s whole power d. And if you randomly pick the input, the probability that the polynomial agrees with the function is at least 3/4. Okay, so that is what I wanted to show in this lecture. Okay, and in the next lecture we will contradict this, meaning we will say that so what we have shown now is that we first showed that every AC0 function can be approximated by a low degree polynomial over f3, and then we actually showed now that every AC0 function, there is a specific polynomial that agrees with the function on 75% of the inputs, where the polynomial is also low degree. But then we will see in the next lecture that parity requires a large degree. So that will be the contradiction. Okay. So just to summarize, we motivated why it is important to have circuit lower bounds. Then we saw the intuition as to why parity may be the right function. We saw how for circuits of small depth, we saw that the size has to be large if they were to compute parity. In fact, matching the bound by Hostad. And then we set out proving the Rasberov-Smolensky result. We first saw the notion of random polynomial approximating a function. We said that a polynomial has a function has can be computed by a size S and depth D circuit. There is a polynomial and a distribution, or there is a distribution from which if you choose a polynomial, this polynomial will be over F3. So the degree is order log S whole power D, and the polynomial 1 by 4 approximates F. And then we saw that using this result, we actually get a single polynomial over F3 that will agree with the function on 3/4 many inputs. So if you let the input change, so there is no randomness on the polynomial is fixed, then it will agree with the input, agree with the function on 3/4 of 75% of the inputs. And we will see why this is. So if it is an AC0 circuit, right, the size S will be polynomial and depth will be constant, then the degree will be, again I have said this earlier, the degree will be order log n whole power D. And the next lecture we will see that this is a very low degree, and we will see that to compute parity we need higher degree. We have already seen how much degree, how much size we needed, and that will lead to the contradiction.